We're going to go over 3 example problems to represent the distribution of sample means. In this problem, we're looking at young adults, and it's saying that the height of young adults follows an approximate normal distribution with a mean of 68 inches and a standard deviation of 3 inches. So I'm going to draw just a little graph here. Before I even actually look at the problem, I'm just going to draw a little normal distribution curve. I'm going to write the mean as 68 inches, and our standard deviation is 3 inches. And so what we're trying to find is how likely is it that a random person is taller than 71 inches. So this is problems that we actually already uncovered. We already kind of went over situations like this, where we're a full number of standard deviations away, right? If we were to calculate the z-score for the value 71, our z-score formula is x minus mu over sigma. And so here our value is 71, our mean is 68, and our standard deviation is 3. And we're looking to calculate how many standard deviations is 71 away from 3. And if we were to do this out, we would get the value 1. So what I'm going to do is I'm going to draw another distribution, our z distribution. Right? And if we wanted to find the probability and percentage associated with being 1 standard deviation, this means we're in our z-score world. Right? So all of these are z values, and these were our original x values. And we're trying to find the likelihood of being greater than a z-score of 1 or the value 71. And so if we wanted to find this area out, right, we're looking for all this shaded stuff. Everything greater, what's the probability of a person being taller than 71 inches? Well, what we do is we know that within 1 standard deviation is 68%. So we're not trying to find that stuff, we're trying to find all the stuff over here. So what's left is we have 100%. In total, something has to occur. There's 68% in the middle. And we're not interested in all of that because that would represent both of these sides. We're only interested in a half. So we'll divide this by 2, and then we'll end up with 16%. So this shaded area is 16%, right? And this is a problem we did before. But I wanted to go over a problem like this to represent how the distribution of sample means is going to change things. So here we have essentially an identical problem, something that in a test or quiz you might confuse yourself with. Here we're finding the probability that the mean of 9 random people is taller than 71 inches. So it's the same value we're interested in. We're still interested in the value of 71. I'm going to draw a distribution right here, but I'm not going to draw the shape yet. Our mean is 68, and we're still interested in the value of 71. The only difference now is, now that we're dealing with the mean of 9 people, the more observations we have, the smaller our spread is going to become. So what's going to change in this problem is our spread. And we're going to denote the standard deviation now as sigma x bar, which we called the shorthand word the standard error, the standard deviation of a sampling distribution. This one specifically is the standard deviation of a sample mean. And if we remember to calculate our new spread, it's actually a function of our original distribution spread and our sample size. So the original spread of this problem was 3 inches, and what we're doing is we're sampling 9 people. So our new spread becomes 3 over 3, which will come out to be 1. Our standard deviation average distance from the mean for our new distribution is 1. And if we look back at the previous problem, we'll notice our original standard deviation was 3. Now it's 1. Our spread has shrunk. So I'm going to kind of draw this distribution out to have a more narrow spread. If we remember, our mean stays exactly the same. We call that mean mu x bar, the population mean of our sample means, because every single observation in this distribution represents a sample mean. So what we'll do is we'll calculate our new z-score. Our new z-score is still saying how many standard deviations away from the mean is some value. But now our value is a sample mean. We're interested in a sample mean being 71 inches. We're going to see how different our sample mean is from the population mean of those sample means. And we're going to put it all in terms of our standard error, which again is a standard deviation of our sampling distribution. So if we were to do this out, the only thing numerically that's changing in this problem is your spread. We're still interested in the value 71. Our mean is still exactly 68. And what's changing is our spread. And if we were to do this out, we would end up with a z-score of 3. So now this value 71 is 1, 2, 3 standard deviations away from our mean. And if we put this in terms of a z-score, right, which we just created, right, in our z distribution world with mean 0, standard deviation 1, we're now interested in being 3 standard deviations away. 1, 2, 3. And we're going to try to find all of this area, which is going to equal exactly this area. So what's nice is that when you standardize your values, your distribution does not change, right? We're still dealing with this standard normal distribution, right? This distribution right here, same mean, same standard deviation. What's changing from problem 1 to problem 2 is the value we're looking for. We were interested in 1 standard deviation. Now we're interested in 3 standard deviations. In our x graphs, right, what's changing is not the value. We were interested in 71. And on our original problem, we were interested in 71. What's changing is your spread, the actual shape of your distribution. We had a spread of 3, a standard deviation of 3, and now we have a standard deviation of 1. So if we wanted to calculate this out using our empirical rules, we know within 3 standard deviations is 99.7%. We don't want that stuff. We want just this half of that outside area. So we'll take 100 minus 99.7, and we end up with 0.3%. But we don't want all of that because that's some stuff over here and some stuff over there. We just want half of that, so we'll divide that by 2. And we end up with 0.15%. There's a 0.15% chance that the mean of 9 random people is taller than 71 inches. We'll do one more problem just to kind of represent our spread. And now we'll look at the probability that the mean of 25 random people is greater than 71 inches. So again, we're still interested in that same exact value, 71. That's not changing. What will be changing is our spread. So now our original standard deviation was 3, but now our sample size is 25. We're interested in the mean of 25 random people. And this is going to come out to equal 0.6. And the mean of this distribution is 68. So when I draw this out, it's going to have the narrowest spread. Super small spread. And when we find the z-score associated with this value, we're still interested in 71. We have the same exact mean, but now our spread has shrunk to 0.6, and we end up with a z-score of 5. And so we'll go to our standard normal distribution, which again has the same mean and same standard deviation of 0 for the mean and 1 for the standard deviation. But now we're interested in being 5 standard deviations away. 1, 2, 3, 4, 5. And all that stuff, if we wanted to just use our empirical rule, we're beyond 3 standard deviations. So we'll just say that's approximately 0%. There's approximately a 0% chance that the mean of 25 random people is greater than 71 inches. Now we can kind of visualize what's going on with the distribution of sample means when we apply it to a specific problem.